the three solutions with respect to the environmental impact. It's just one decision. Okay? On the basis of the information that I had before. First of all, if we go back to the information, you easily understand that you don't need a complicated method for taking this decision if you have just the environmental impact as criteria. Because if you look at the information related to the environmental impact, there is a solution that corresponds to clearly the lowest impact. And therefore it's clear that we will have to select river cross-section 30. Okay? So let's apply now a complicated method to take a straightforward decision to see if the method works, at least with a straightforward decision. Now, you can guess that the decision is taken by comparing the solution 2 by 2. So let's see how we can do that. And this is a pairwise comparison. And what we have to do is to compare the solutions 2 by 2 according to this scale, suggested scale of comparison. So let's suppose that you compare river cross-section 10 with river cross-section 25. And according to the selected criteria, which is environmental impact, let's say that we assume that river cross-section 10 with respect to the 25th, if they are equally important with respect to the criteria, if they are equally preferable, we give a score of 1, which is the importance of the solution corresponding to river cross-section 10 with respect to the importance of the solution given by river cross-section 25. And the reciprocal is true, meaning that if 10 has an importance of 1 with respect to 25, it means that also 25 has an importance of 1 with respect to 10. Instead, if you think that 10 is moderately preferable with respect to 25, and it's identified here as moderate importance with respect to the criteria. So I say again, if you think that 10 is moderately preferable with respect to 25, you then would assign a score of 3 to 10 with respect to 25, which means that 25 with respect to 10 will have a score of 1/3. It's a symmetric evaluation. When you make a pairwise comparison and you say that one solution is better, it means that the other solution is worse. So if you say that the importance is 3 of the first with respect to the second solution, then the importance of the second solution with respect to the first is 1/3. And you can use also an intermediate scale. You could say 2. Let's say that 1 is equal importance, 3 is moderate importance, 5 is strong importance, strong preference, 7 is very strong preference, and 9 is extreme preference. This is just an agreement in order to express our preference in numerical terms. So you can already recognize an attempt to convert a preference into numerical value by using this agreement. And here you can see that intensity of 2, 4, 6, and 8 can be used, and also you can use decimals if you wish. It becomes complicated because, you know, already deciding if an alternative with respect to another is moderately preferable instead of strongly preferable is not easy. And then if you want to to go into more details is not so easy. But we may need, as we will see, to use also intermediate numbers.
It's really subjective, no?
Yeah,
I mean, I can say that 10 respect to 25 is for me 5, and you can say that is for you 3.
Yes, this is of course true, and in fact, this is why I said that you need to take this decision with your stakeholders, because you need a consensus, to reach a consensus among them. And reaching a consensus is much easier if you take the comparison 2 by 2. Because if you move to 3 by 3 already, you will see that it's very difficult to reach the consensus. Instead, if you put together some people and it's just a comparison by 2, it's much easier to reach the consensus. And as a general rule, keep in mind that basically you should take a different approach with respect to what, for simplicity, I'm taking here. So you should discuss the importance before knowing the information in some cases. Like, for instance, in this case, you can't do that because you have to decide between different locations and therefore you need information for that. But for instance, when you discuss the importance of the criteria, and we will make this discussion later on, so basically you have to decide whether the cost is more important than the environmental impact. It's better to take this discussion without giving any preliminary information on the behavior of the sites, because otherwise one involved person which is interested in having the dam at a given site, he immediately converts the information into his preference related to the site. So basically each decision should be taken by using only the information that is related to that decision. And so basically, to give you an example, again, when we decide to enroll new professors, we first discuss the criteria and then the information of the candidates. So first of all, we say it's more important that a professor teaches well, or it's more important that he is able to attract a lot of funds, of funding, research funding, and then we discuss about this. And then we present the information about the candidates, because if you present the information before then taking the decision, then the decision becomes even more subjective. Okay, now, the problem that we still have to afford is to put the outcomes together. So basically, let's refer to our example now. And remember that we have to evaluate the environmental impact. And so let's give a mark according to this table. So let's compare cross-section 10 with cross-section 25. And you may remember that, let's look at the information again, because information related to environmental impact. And you can see it here. So cross-section 10 is very impacting. Cross-section 25 is in between. And cross-section 30 is the less impacting. Okay? So this is what we wanted to say. So basically, if we compare our preference in terms of environmental impact for cross-section 10 with respect to 25, what would you expect? You would expect that the ranking is below 1. So 10 with respect to 25 in terms of environmental impact would be 1/3, 1/5. Okay, because the impact is higher for 10, and therefore you don't want it. Okay, let's see if I am consistent in my evaluation here. So basically you see that I'm comparing 10 with 25, and I give a mark of 1 and 3. So it means that for me, it has a moderate importance, 25 with respect to 1. Okay, 25, remember, it was in between in terms of environmental impact. And then if I compare 10 with 30, I give an higher score to 30, because 30 is the solution with the lower impact. So in order to be consistent, I have to give a score of 30 with respect to 10, which is higher than the score of 25 with respect to 10. I wouldn't be consistent in my evaluation if this score was not higher than this one. And now we still have to compare 25 with 30. And remember that 30 has the lowest impact, so I have to give an impact, a strong preference to 30 with respect to 25. So basically, if I compare 30 with 25, I have a strong preference and a very strong preference with respect to 10, which is consistent. Okay? This is very easy if you make the comparison 2 by 2. But of course, you need to take into account in the subsequent comparisons the outcome of the previous ones. So you already understand that if you have 10 alternatives to compare, then you have to be careful on what you do in order to be consistent. And the result of this evaluation is better visualized into a matrix. And here is the matrix of the decision. So this is a symmetric matrix, and it's a diagonal matrix. So basically, you have in the columns and the rows the alternatives. So if you compare 10 with 10, of course, they have equal importance. It's 1. If you compare 10 with 25, it's 1/3, because we said that 25 is preferable. If you compare 10 with 30, it's 1/7. Then let's compare 25 with 10, it's 3. It's symmetric. If it was 1/3 here, then it's 3 here. And then 25 with 25 is 1. 25 with 30, it should be 1/5. Because 30 is much better. And therefore, if we go to 30, it has an importance, a score of 7 with respect to 10, and a score of 5 with respect to 25. And you see, it's symmetric. So this is the result of our evaluation. And now, from this matrix, we can compute, we can give a weight to each alternative. And this is the interesting development. By processing this matrix in a way that I now will show you, you can give a weight to each alternative. When I say that I give a weight to the 3 cross-section, I imply that I give 3 scores. The most preferable one will have the highest score, and the sum of the scores will be 1, because they are weights. So if I find this method of giving a weight to each alternative, then my decision is taken, at least for this very simple case. Okay, let's see how we can do that. We have a matrix here, which is symmetric, and we don't prove it, but we take this statement for true. Basically, these weights or priorities are given by the principal right eigenvector of the matrix. So I know that you are getting a bit desperate now, because when one speaks of eigenvector, eigenvalues, which in Italian are autovalori, autovettori, one gets a bit lost, especially if he's and she's an engineer, because a mathematician, of course, manages eigenvalues and eigenvectors very easily, and for us it's a bit more complicated. And basically, we don't have to despair, because with R it's very easy to compute this right eigenvalue and eigenvector. And as I have written here, these values can be calculated in many ways, including by hand. It's quite easy. And or they can be computed in R. And here I'm also mentioning a software which probably I should remove this mention, because it's not a public domain software, it's a commercial software. Okay, now, just in order to be more clear, what is the right eigenvalue or right eigenvector of a matrix? Basically, I think I put a definition here. Basically, if you indicate with n the number of alternatives, so in this case n is equal to 3, the right eigenvalue, and if you indicate this matrix with the symbol A, the right eigenvalue is such, eigenvector, sorry, is such that if you multiply this matrix A times the eigenvector you get as a result n multiplied by x, where n is the dimension of the matrix or number of alternatives. So you see that the definition is easy, indeed. So it's a vector that if you multiply it on the right side by the matrix, you get as a result the same vector times the dimension of the matrix, which is symmetric. Now, how to yeah?
Is that matrix symmetric? Because
antisymmetric, sorry, antisymmetric. It's diagonal antisymmetric. Correct. I was not. I was wrong. It's antisymmetric. But anyway, it possesses the eigenvector anyway. This eigenvector contains the eigenvalues of the matrix, and there will be value of among these eigenvectors which we identify with the symbol lambda, which is the max. Lambda is the max of x. And let's just keep this symbol in mind for what follows. Now, how can we compute this in R? In R it's very simple, and here is the code. And basically, first of all, there is the definition of the matrix, and I used this way to define this matrix. So I went by rows. I entered first a vector. You see PR1 is a vector where I put the elements of the matrix by rows, and then I convert in the second instruction the vector into a matrix whose dimension is 3 by 3. And then I take the transpose, because if I go by rows in entering the values into the vector, I need to transpose it in order to get the matrix in the right way. And this is the visualization of the matrix in R. And you see that it's 1, 1/3, 1/7, and etc. And it's antisymmetric. So this is the matrix. Then the function to compute the eigenvalues is eigen. And we need to specify that the matrix is symmetric, or antisymmetric is the same story. And we need to specify it anyway. And then the weights are computed in this way by using the function mod, is the module of these vectors. And there is this adimensionalization in order to make sure that they sum to 1. So in order to make sure that these weights sum to 1, I need to divide the 3 weights by their sum. And you may say why they don't already sum to 1, because if I said that the weights are given by the eigenvector, you may tell me why they don't sum to 1, why you want to make sure that they sum to 1. Okay, the reply will come in a couple of minutes. Okay, that's fine. In fact, if you take the sum of the weights, you get 1, and these are the weights. And basically what we see is that the cross-section 30, which is the third one, is given a weight of 0.73 versus lower weights of 0.19 and 0.08 for the cross-section 10 and 25. So basically the preference goes to 30, and then to 25, and then to 10. Is this correct? Let's go back to the information.
Non so, ma no.
If they don't sum, there is a mistake by me. Let's see, just in 1 second. You see that, in fact, cross-section 30 is the one with the limited impact. And then we have 25 in between, and 10 with high impact. So, of course, the result is fine. And now let me see if they don't sum, which is strange. Maybe that I made a mistake in... no, it's fine. I think it's fine. 0.73 plus 0.19 means 0.92 plus 0.08, they sum to 1. Correct? Okay. So basically what we saw now is that the outcome is consistent with our perception, which proves the validity of the method. But now let me introduce a discussion. What if my evaluation is not consistent? What if in computing, in putting together this matrix, I change, for instance, this value of 7 to 5, which means that I should also change to 1/5 this evaluation. It wouldn't be consistent, because if you think of the available information and your previous decisions, it wouldn't be consistent. So basically, if you say that 10 has an importance of 1/3 with respect to 25 and 1/7 with respect to 10, when you compare 25 with 30, you would expect that 25 is less important than 30. So 1/5 is okay, but I could put here 1/7 or 1/9. And of course, there are 3 alternatives, or 4, because I could also decide 1/3. And of course, some of these alternatives are more consistent than others. So if I look at the proportion between 1/3 and 1/7, my perception is that 1/5 could be the correct interpretation. Because you see that 30 is much more important than 25 when both compared with 10. So, okay. I guess that 1/5 is a consistent evaluation of 25 with respect to 30, but is it really correct? I need to make a check of this. Because if I change this number from 1/5 to 1/7, the results change. So how to check for consistency? And a way to check for consistency is given by the definition of the weights. They are given by, as I said, the right eigenvector, and they should sum to 1. If they don't sum to 1, they are not consistent. And also there is another condition which is important to note. This lambda, which is the maximum of this value in the eigenvector, this lambda should be very close to n, to the dimension of the matrix. And meaning if the matrix is fully consistent, it should be equal to the dimension of the matrix. Okay, now, how can we check then the consistency? So in an ideal case, when the matrix is fully consistent, if you read here, we see that the eigenvector represent the weights we are looking for. If we are not consistent, basically the matrix A can be considered as the perturbation of a consistent matrix. And therefore, the eigenvalues that you get do not correspond to the weights. So basically the condition this is the normalization that I introduced, because of course, you know, you will never get a fully consistent matrix. There will be some inconsistency. So basically, first of all, let's make sure that this weights sum to 1, because by definition they have to sum to 1. So even if we have some inconsistency, they have to make sure that they sum to 1. And let's define at this point this quantity, which is named Ci, which is given by lambda minus n, should be 0 if the matrix is fully consistent, divided by n minus 1. And again, this Ci should be 0 if the matrix is fully consistent. And if it's not 0, there is some inconsistency. And therefore we have to evaluate if the inconsistency is tolerable. So we have to compare the value of Ci with the reference value. And there is one problem, by the way. Basically, this reference value, or the consistency index Ci, depends on the size of the matrix. Because if you have a matrix that is very huge, of course you are more likely to be inconsistent. And therefore, basically, you have this Ci, you have to make it a dimensional in order to have a reference that is more or less independent of the size of the matrix. And basically, you obtain this target by dividing the Ci by a reference value which only depends on the size of the matrix and is given by this table. And just read the description of how this table is computed. Basically, it's a reference, it's a value that is given in the form of a table, and for me it's just enough that you remember that it's a reference value that depends only on the size of the matrix, and it can be used to make the consistency index independent of the size of the matrix itself. And then we can conclude that if the result of this ratio is lower than 0.1, then the matrix is assumed to be consistent. This is not so easy to get, but in order to perform it in R, the solution is very simple. And if you move forward in the document, there is here there is the code. Basically, you have to compute PR2. Remember that PR2 is your eigenvector. And if you compute the module of this eigenvector, you get these three values, and you see that I have a value of 3.06. I told you that a value of 3 would mean that the matrix is fully consistent. I have an higher value of the maximum of the module of these eigenvectors, and therefore I need to compute the consistency index to see what happens. And basically, I can write that you can see here the computation of the consistency index, and then there is the consistency index that is divided by the reference value in order to make it a dimensional, independent of the size of the matrix. And you see here that the result is 0.05, which means that the evaluation is consistent. Perfect. Okay. Now, where we are now, basically we are at the stage in which, sorry, I go back. I found the weights to be assigned to the three alternatives according to the environmental impact. Okay? And now the problem is solved if our problem is just to identify the solution in terms of the three river cross sections that corresponds to the more limited environmental impact. Our problem is solved. And this is a problem that, of course, is straightforward because we considered only one criteria. If we want to consider the other three criteria, I have to repeat the same method for classifying the alternatives with respect to the other three criteria. And then I have to identify the weights to give to the criteria for coming to a final result. And this is described in what follows. Okay. Now I'm moving forward in the document, which reports the evaluation of the three alternatives with respect to the other criteria. So the next one is, I move forward, the next one is, you see, now you have the four criteria, you have a hierarchy of decision, the four criteria, and the evaluation of each alternative with respect to each one of the criteria. And this is a repetition of the information that I had at the beginning. And now let's compare the sites with respect to the reservoir cost. And look at the cost of the reservoir. It's the most convenient option is river cross-section 25, and then we have 10, and then 30. So we expect that the higher weights now corresponds to the section 25, followed by 10, and then 30. And here I have again the matrix, again the weights. Basically I have a weight of 0.75 for cross-section 25, 0.18 for 10, sorry, there is written 17 there, it's 10, and 0.07 for 30, which is fine. This is what we expected. And the consistency, it's again fine. Okay, now let's look at the storage. And if you look at the storage, this is the matrix. And then the weights are cross-section 10, which is the one that has the highest storage, is given a weight of 0.79. And then the other two cross-sections have 0.06 and 0.15. Again, the evaluation is consistent. You see that a different preference is assigned to different criteria. So if you look at the cost of the reservoir, you select a solution. If you look at the storage, you select another one, of course. And then we have again the comparison with respect to the landscape impact. This is the matrix. And you see that cross-section 10 is assigned a weight of 0.71 versus weight of 0.07 and 0.22 for the other two cross-sections. And I just want to go back now to the information to check that cross-section cross-section 10 is the one with the most limited landscape impact. I just want to go back to make a check. So I'm now going back, and you see that, yeah, the landscape is not impacted for cross-section 10. So this is fine. Okay, so basically now we have, I go back to the evaluation. Here there is an important thing to see. CR is higher than 0.1. It means that this matrix that you can see on the top is not consistent. And I should change it. I didn't do that. I just wanted to keep it because I wanted to show you that you can easily get an inconsistent matrix. So if we wanted to be very rigorous, we should change it. If we keep it in this way, we still have weights. They sum to 1, but they are not, strictly speaking, correct. So if you make an inconsistent evaluation, you end up with wrong weights. Of course, in this case, I can say that 0.15 is close to 0.1. I can accept it. You can easily get to values of CR of 0.9 if you play with it. It's not difficult to get high value. Now we have the key of the whole story. Look at the bottom. We have to compare the criteria each other. And this is a key step because basically so far we took decisions that individually they are very straightforward. In terms of identifying what is the best solution for each criteria, you could do that just by intuition. Of course,